Hello and welcome. My name is Julius Grüding. I'm from the Justus Liebig Universität in Gießen, where I do a PhD with Ralf Köhl. This video is a contribution to the NCNGT conference, and I want to thank the organizers for organizing the conference. So, without further ado, let me just dive right into the topic that I want to introduce to you, which is Moody symmetric spaces. Moody symmetric spaces, they are generalizations of Riemannian symmetric spaces of the non-compact type. And to be able to explain to you the definition, I must first explain to you the definition of Moody groups. And to be able to do that, I must first introduce you to Moody Lie algebras. Now, as the spaces are infinite dimensional Riemannian symmetric spaces, so to speak, these Moody groups, they are infinite dimensional Lie groups, and these Moody Lie algebras, they are infinite dimensional Lie algebras. And to really be able to explain to you these Moody Lie algebras, I want to explain a little bit about the classification of semi-simple Lie algebras of the complex numbers via Dünken diagrams or Cartan matrices. Dünken diagrams and Cartan matrices, they are equivalent notions, and you can classify semi-simple Lie algebras over the complex numbers by them. And I don't want to explain to you how the classification works or the proof or anything. I just want to talk a little bit about the result. The result is well known. It's called A, B, C, D, E, F, G. And it's these graphs, okay? These are the Dünken graphs, the Dünken diagrams. And here on the left side you can see the corresponding matrices. One thing, the matrices always they have 2's on the diagonal. All other entries, they are negative or 0. And the correspondence is as this: you for every, say, diagonal entry you have 1 dot, and you draw a line between 2 dots. If there is if there is an entry that's non-zero, okay, and if it's 1, you draw a single line. If it's -1, if it's -2, you draw a double line, and then when you draw a double line, then you have to add the direction, and it's whether the -2 is on the lower triangular half of the matrix or on the upper triangular half of the matrix. And take note that this is quite restrictive, yeah? All of these diagrams, you could say they're almost all straight lines. The first one, AN, is a straight line. This one corresponds to the Lie algebra SLN. Let it be the prime example for this talk. And all other lines, all other graphs, well, they are almost straight lines, okay? Some have double bonds, one has a triple bond, and two families, they have branching points, but that's it really. Okay, so the classification of semi-simple Lie algebras over the complex numbers tells you that given any let me be more precise. Given any simple Lie algebra, okay, these are the simple ones, the semi-simple ones then are direct sums of these. Given any simple Lie algebra over the complex number, one can associate such a graph or such a matrix uniquely such that two Lie algebras are isomorphic if and only if their Cartan matrices are the same. Okay, that's the classification, and now what is actually a Cartan matrix? I've written it on this slide. A Cartan matrix is a matrix satisfying 4 properties. First property, I told you already, all the diagonal entries are 2. Second, I also already told you, all other entries are less or equal to 0. Third property, one entry is 0 if and only if the transposed entry is also 0. And the fourth property is really the property that makes this list so restricted. You could call it sphericity property or finiteness property or finite dimensionality property. It says that the Cartan matrix is invertible and that there exists a component-wise positive vector such that if you apply the Cartan matrix to this vector, it stays component-wise positive. And if you have if you have a vector v that you apply the Cartan matrix to and it is then component-wise bigger or equal to 0, the vector had to be component-wise bigger than 0 or equal to 0 in all components. Okay, so these are Cartan matrices, and let me put them right here. Okay, so much about the classification, and what I'm really interested to talk to you about is the converse classification, not the classification of Lie algebras via Cartan matrices, but classification of Cartan matrices via Lie algebras, which is a celebrated theorem by Serre. And it says the following thing: let A be a CM, a Cartan matrix. Then the theorem constructs a Lie algebra via generators and relations. I'm going to explain them in a second. And then the conclusion of this theorem is this so constructed Lie algebra is the semi-simple Lie algebra with Cartan matrix A. So you begin with the Cartan matrix, you construct a Lie algebra, and it's exactly the Lie algebra that you wanted. Okay. Whoopsie. Okay, how does these relations and generators and relations work? Well, say you had an n by n Cartan matrix. Then you would take 3n generators, ei, fi, hi, and I runs from 1 to n. And then you introduce the following relations. Hi and hj should commute. So these h generators, they form a commutative subalgebra called the Cartan subalgebra. You have that the commutator of ei with fi is hi, and you have that ei and fj commute if I is not equal to j. Then you have that the commutator of hi with ej equals aij, which is the Cartan matrix entry, times ej, which goes to say that the action of the Cartan subalgebra on these ei and ej symbols is diagonal. And you have the same thing for Fi, or Fj, sorry. The commutator of Hi with Fj is Aij times Fj. What's remarkable about these two is that you don't really need anything of the Cartan matrix. Here I've specified that it has to be a matrix with integer entries. It's not needed here. Aij could be a complex number, for example. And all the other properties, we also didn't need them to construct this Lie algebra. For the third row of relations, we need at least, I believe, the second property. What this says, and these relators go by a special name, they are called Serre relations. They say that at Ei to the 1 minus Aij applied to Ej equals 0. And the same goes for Fi. So at Fi applied 1 minus Aij times to Fj gets 0. So it's, you could say, a nilpotency relation. Okay, as I mentioned, okay, here at least you want the Aij to be negative integers. So to be able to do this construction, you don't, well, you only really need that they are integers and that they are lesser and equal to 0 when they are not on the diagonal. Okay, and well, this is then the entry point for Kac-Moody theory, because what one can now easily do, as this construction doesn't really want anything of our matrix, we can easily generalize by, well, removing what I have glued to the top here. And now what it says definition of the Kac-Moody algebra, and we begin not with a Cartan matrix, but with a generalized Cartan matrix. Okay, I'm going to explain in a minute. We construct the exact same algebra, and of course the conclusion is not that this is a semi-simple Lie algebra with Cartan matrix A, because, well, it isn't, but this is then the definition of the Kac-Moody algebra. So the conclusive sentence of this card is, this algebra is now called a Kac-Moody algebra associated to the generalized Cartan matrix A. Now, here I have Cartan matrix. Now, what's the generalized Cartan matrix? It is almost the same. Well, the first three properties are the same, and the fourth property isn't there anymore. Instead, there's another property that's useful, and that's also needed for this definition to be equivalent to another definition that I didn't show you. So, okay, I put it on the slide as well. And it's called symmetrizability. And it means that the Cartan matrix is a product of two other matrices, namely a diagonal matrix and a symmetric matrix. Okay, and now we not only have A, B, C, D, E, F, G anymore, but we have far more. So let's have some examples here. For example, if we take the Cartan matrix to be a 2 by 2 matrix, these conditions, everything, also including the symmetrizability condition, are met if we put the matrix 2 minus A minus B, 2, with A and B natural numbers, such that A times B is bigger or equal to 4. these algebras associated to these Cartan matrices are called rank 2 hyperbolic Kac-Moody algebras. Now the next example is more famous, I'd say, is when you make a circle. Note here in these, I mentioned in the beginning, they're almost all, well, straight lines, they're very close to straight line, and no circle ever appears, because circles already make the algebra be infinite dimensional. So what comes out if you take this circle is then SLN of the Laurent polynomial ring. Okay, I plug the real numbers here. You can do this for any field, but okay, there's the real numbers here, just for convenience. And these are called the affine Kac-Moody algebras. They're probably the most famous among the Kac-Moody algebras and the most studied because, well, they're the most accessible, I'd say. And this works not only for SLN, there's a way to extend any of these ABCDEFG algebras to an affine Kac-Moody algebra, and then we will just have to replace SLN by the corresponding Lie algebra functor and plug in not the field but the ring of Laurent polynomials over the same field. Okay, the next one's a little bit of a joke. I drew this house of Santa Claus. So this is a celebrated Santa Claus Kac-Moody Lie algebra. But what I just wanted to say with this, you can really draw any simply laced graph and get an algebra, and it will meet all the conditions of this. So if you don't have any double bonds or triple bonds, like for example G2 has a triple bond, then you can draw any graph and all these conditions will be met. If you want to have complex graphs with also double and triple bonds, you will have to be careful with the symmetrizability condition, but alright, okay. And then the last one is not an example, but a property that is important later on. It's called two-spherical, and this means that all standard rank 2 subalgebras are finite dimensional. Now what's, okay, let me quickly put this here. Now what's the standard rank 2 subalgebra? It's explained very easily, but let me begin with standard rank 1 subalgebra. Is you pick one I from your list 1 to n, and you take the triple EI, FI, HI for this specific I, and this generates a subalgebra called the standard subalgebra associated to this I. And if you pick two, I and j, and generate a subalgebra by these two triples, EI, FI, HI, and EJ, FJ, HJ, you will get the standard rank 2 subalgebra. Alright, now that I have explained to you these algebras, I can now reveal the definition of Kac-Moody groups. Okay, namely it works the following way. The only thing you do is you take, okay, let me say one more thing. I'm only going to define the adjoint Kac-Moody group because that's the simplest thing you can do. There's also a bigger story evolving around the definition of Kac-Moody group, and, but this is a shortcut, or the shortest thing you can do, and the only thing you do is you times the adjoint action of these generators EI and FI with some real parameter t. Okay, it doesn't have to be the real numbers, but here it is, and then you apply the exponential series, and this is then an automorphism of the Lie algebra. And the beautiful thing is that this really works. And why does it work? Well, let's look at the exponential series again. It's the usual thing. You take it to the nth power and divide it by n factorial and sum over all natural numbers. And the thing why this works is exactly in the Sarah relations. I told you these are sort of nilpotency relations, but they work out not to be then nilpotent operators, but only locally nilpotent. Okay, video stopped for some reason. Okay, they are not nilpotent operators, but locally nilpotent operators. Which means that for every x in the Lie algebra, there exists a natural number n depending on the element x, such that the adjoint action of ei applied to applied n times to x is 0. But okay, so this is not nilpotency because this natural number is not global for every x, but depends on x and grows with. Oh, if you pick, say, the wrong sequence, this nx will grow with x. Short thing that I forgot to mention in the original recording. This local nilpotency then implies that this exponential series, it stops, it's a finite sum. And that's why it's a well-defined function. It's just that when it stops depends on the point that you plug in. Okay. And now I want to introduce one more thing to be able to reveal the definition of Moody symmetric spaces, namely which is called the Cartan-Chevalier involution. And it's two involutions really, or well, one on the algebra, one on the group, but they're really the same thing. On the algebra what you do is you send ei to minus fi. And of course fi is sent to minus ei. And hi is sent to minus hi. This then works out to induce something on the group. Okay, and now you have an involution on the group, which is fantastic because then you can define what is, or what you could call, the maximally compact subgroup of the Moody group, which is just the fixed point set of this Cartan-Chevalier involution. Now, maximally compact isn't the right word because it's not compact. It's only really compact if the spaces are finite dimensional. We are talking about the infinite dimensional ones, so maximally compact is plain wrong, but by analogy to the finite dimensional situation, I just called it maximally compact here. Okay. And now that we have this, I'm ready to reveal the definition of Moody symmetric spaces. Namely, these spaces X, they are just a quotient space G mod K of the Moody group via its so-called maximally compact subgroup, like it is in the finite dimensional situation of Riemannian symmetric spaces of non-compact type. And this curious formula here, I am going to leave it for a cliffhanger for the next video. Thank you so much for watching and see you in the next video.